and welcome back to the Meteorologists Podcast, the podcast where we follow the fascinating stories behind the people that shine in the history of meteorology. Today we are stepping back to 505 CE to meet a man who is to forecasting what most of our episode subjects have been to maths, Varāhamihira. But first, actually, I won't tell you a long story about my recent travails at a conference because I've got some parenting to do. So I'll wrap this one up quick by telling you a small joke that we have in England about buses. You see, in England, we say that buses are a little bit like podcasts about mathematical figures in history. That is, you wait a whole month for another one to come, and then two come at once. That's right, folks. Today we are doing my third double bill with two mathematicians. But let's start with Varāhamihira. Born in Malwa, Western India in 505 CE, Varāhamihira is one of the great links in the chain of mathematical knowledge. He is most associated with the city of Ujjaini, from the same community as Yavanasavara, the Lord of the Greeks, from episode 57. You might remember that long exposition of Indian political history from that last episode. Well, today we meet Varāhamihira right at the tail end of the Gupta Empire. Much like today, turbulent politics does not always mean the decline of academic endeavour. Sometimes the uncertainty provides the space and the pressure for new ideas. The biographical record is patchy, but we have a few clues scattered amongst his work. His father was linked to sun worship, possibly his first tutor in science. The standard syllabus of the day was arithmetic, geometry, astronomy, astrology, Sanskrit, and religious traditions. He worked in the same city as Yavanasavara, only a few centuries later. This means he would have been well acquainted with the, quote, Greek science, and seen the adaptation and progression through the work of Yavanasavara and later authors. He is quoted as saying, "The Greeks may be foreigners, but they should be honoured because they excel in science," which sounds not too dissimilar to the UK's current approach to immigration. Varāhamihira is most known in mathematics for his contribution of the scholarly encyclopedia Pañcasiddhāntikā, or the 5 astronomical systems. This is a major work of archivism, and without it, much of our knowledge of the previous mathematics would be lost. To accompany this, he also wrote a major treatise on astrology, the Bṛhat Saṃhitā, which is less interesting to mathematicians today. But aside from these two huge texts, he is most universally famous for his 100 chapters of the Bṛhat Saṃhitā, an encyclopedia to cover every topic that he decided himself an expert on. And it is this work that I'd like us to begin with today. We should remember that whilst all of our philosophers are philosophizing and our mathematicians are mathematicalizing, the primary driver for people for much of history has been bare survival. A man's got to eat. And whilst it is traditionally a marker of a city moving into civilization, ignoring for a moment the problematic nature of that phrase, that a culture might diversify into food producers and or specialist roles, the main utility of the specialist roles is to support the population in some way. A tanner helps make leather for the warmth and comfort of the people. A farrier shod hooves, and I'm sure that's a helpful thing for them too. Just don't ask me why. So what can a mathematician actually give to people, aside from infrastructure, projects, architecture, and astrology? What can a mathematician give to the ordinary peasants of the land? Or, to put it another way, what did the Romans ever do for us, aside from all of those things? Farming advice? Sure. Specifically, in the Great Plains of North India. This relates to the monsoon. We discussed the monsoon in our episode of Yavanasavara, in terms of its help for the sea trade, but the monsoon has a life-sustaining impact on agriculture as well. Being able to predict when the monsoon might arrive, how long it might last, and whether it will be a good or bad rainy season, well, this is information, and information is worth power. Naturally then, Varāhamihira turned his attention to the sky. He conducted a survey of ordinary people and collated generations of observational data about the sky and weather patterns to try to find some common thread. He asked people to describe the shape, height, and colour of clouds, and how quickly they formed, and which way they went, and whether they were layered or isolated. What we have then is clearly somebody studying geography, but arguably an early entry into the world of statistics. Now, most grown-ups can predict what the weather will be like on a given day. You can see rain clouds, you pack an umbrella. It feels hot and sticky and thick in the air, you might expect thunder later. This short-term intuition is something we pick up naturally. What Varāhamihira attempted to do was to extrapolate data to long-term prediction months ahead to give local kings and rulers time to prepare for good or bad monsoons. And these climactic indicators are still tools that modern meteorologists will use, albeit his foundations came from traditional experience rather than controlled experimentation. My favourite description of his clouds is whether they are pregnant or gestating the rain. He believed that the clouds conceived the rain, spent several months holding that rain until eventually they could give birth to rainfall. But perhaps my favourite insight of his that we could look at is how he didn't focus on clouds and weather as exclusively a skyscape phenomenon, by which I mean his insights also take into account local mountains or rivers or other geographic features, which do very much play a part in weather formation. As listeners will know, I live in a coastal region of Dorset, home to Britain's most envied hills and ridges. You can watch the clouds form at the cliffs on the coast on windy days as the moist sea air rushes into the hills, ridges and cliffs and is forced upwards to condense. Before I praise Varāhamihira too greatly, though, I will rain on his parade and say his work contains some less favourable science, such as astrological omens that may impact the monsoon. Although there is one star in particular that I think does have a big impact on weather, and that is the star closest to Earth. But I'll leave you to do that research yourself. I used to have a friend who was a teacher of physical geography. No, this isn't the intro again from last season. She told me that although weather plays a big part in the study of Earth, in order to study Earth, one must study Earth. Usually at this point, I would just write the words Oxbow Lake and move on to the next question, but Varāhamihira gave a greater level of insight into the ground. I am, of course, talking about water divination. Now, some people would tentatively suggest that water divination, or dowsing, is not a real science. And those people are correct. So before we discuss what Varāhamihira knew 1500 years ago, I'll do a quick expose on what people do not know now. Water is not magic, nor does it have memory. There are no magnetic fields or electrical currents in water that would be able to twitch a wooden stick or cross metal rods or make a pendulum tremble. If there were unknown fields or potentials caused by water that are yet undiscovered by the instruments of physics, then I would posit that neither will these fields or potentials be detectable by a wooden stick, metal rods, or a pendulum. If, however, you were so minded to walk into a field with a wooden stick, metal rods, or a pendulum, and try to identify an area that has groundwater, you would be in luck, because basically everywhere has groundwater. Or rather, groundwater is tremendously abundant if you're willing to dig down deep enough. There is still a $100,000 prize money unclaimed from the 1980s for anyone who can identify water using water divination methods beyond a statistical error of uncertainty. So that's fun. Now, back to things historians know with a lower level of uncertainty, the Bṛhat Saṃhitā. And we get to a real gem of the text, that is to say, his chapter on gemstones. Much of what Varāhamihira wrote on gemnology is still considered fundamental to today's practices, at least in my very real gem shop. So the value of gemstones is dictated by colour, brilliance, clarity, shapes, flaws, size, and of course how foolish the tourists are. He wrote about diamonds, rubies, emeralds, and sapphires and pearls. Why he didn't notice that some of these are actually the same base mineral is a real corundum. In the text, he notes that the benefit of these precious gems go beyond a store of wealth, or high-value currency, but have a mystical existence with beneficial powers. Similarly, we have colourful stories about the origins of the gems, diamonds from when thunderbolts strike the ground. Possibly just a homophone from the Sanskrit vajra, meaning both thunderbolt and diamond, as they are the most irresistible objects in existence. He knew that a pearl came from oysters, as did most scientists of the age, but in his work he notes of folk tales of pearls coming from any and all of elephants, snakes, fish, bamboo, conch shells, and clouds. So choose your own origin story if you are indeed a gullible tourist and you come into my shop. He also documented the protective and healing powers of various gemstones, including linking each stone to a celestial body. In this way, the wearer might be able to encourage a horoscope in the direction of, say, Jupiter by wearing a yellow sapphire. We, of course, should not criticise the ancient Indian thinkers for believing in the healing powers of crystals, as this was an international effort to ascribe power to rocks. After all, the word amethyst comes almost directly from the Greek amethystos, meaning not intoxicated. Personally, I have never got gazeboed whilst drinking from my amethyst shot glass, so go figure. Humour aside, we do see strong evidence of an Aristotelian approach to science, with probing questions around gems to sort them into taxonomies, such as, what colour is it? Is it transparent? Does it have cracks? Is it symmetrical? Where was it found? How should it be classified? He is far more interested in observable characteristics than in elaborate mythical origin stories. You might be wondering then, with all this taxonomy and encyclopediation of the natural world, was Varāhamihira the Aristotle of the Indian world? Short answer, no, and stop trying to compare everything to the Greeks. I've told you for this enough already. A slightly longer answer. Although the drive to create a comprehensive encyclopedia existed in both men, a big difference that splits them is the work on logic itself. Aristotle developed this for the Greeks, but by the time of Varāhamihira, logic was already a well-established discipline. Charmingly enough, the English idiom, "there's no smoke without fire," perhaps the most directly logical phrase in English, takes its origins from the Nyaya school of ancient Indian philosophy. I have said it before, if I ever get the chance, I would love to do the history of logic, so I shall leave that story for the future podcast. As you can probably guess, the majority of the encyclopedic contributions so far have had one clear theme running through them: agriculture. Or at least that might have been clearer if I wasn't mangling the story so much. The primary focus of his work, understandably, was how do we produce more food and resources than we need? The monsoon forecasting and rainfall prediction was central to farming. Land surveillance and topography gave insight into the suitability of soils. This includes mineral composition and is linked to gemstone abundance. Locations of groundwater and identifying trends in trees and ecology all form a picture of a successful plot of land. Agriculture was, and is still, a system, and for those of you who don't like dirty hands or a peg on the nose, you can contribute to farming by being an agricultural scientist. Not all of his advice has stood the test of time, but he was pretty on target with regards to where to look for clues. Whoops, we are about 15 minutes in, and I still haven't started talking about the maths. I mentioned near the top that his primary mathematical contribution was in preserving the 5 schools. So, let's do that. The Doctrine of the Grandfather records the earliest astronomies with traditional beliefs and understandings. This would include simple planetary cycles, inaccurate predictions of eclipses, and ancient calendar methods. Another indigenous system is called the Vasistha Siddhanta, named for the sage Vasistha, not a mathematician. This system had better calculations and parameters for planetary movement, and a more sophisticated computation of the calendars. Together, this is the time of our earliest Vedic mathematicians like Bhaudhayana and Apastamba. Although they are not specifically named, they form the bedrock of these traditions. Jumping forwards in time then, we have the Mathematicians, named after the Romans, probably. This is where we start seeing the Hellenistic geometric systems and Alexandrian computational methods, and crucially a Julian-style solar year. Similarly, we have the Pañcasiddhāntikā, probably named after Paulus of Alexandria, not a mathematician. Again, this has an update of Hellenistic influence on and zodiac-based calculations. The planetary models are similar to late classical astronomy in the Roman Empire, so that's cool. Yavanasavara is not directly associated with either of these schools specifically, but definitely contributed to the broader movement of importing knowledge, so we can tag his name along. The fifth and finally dominant school was the Surya Siddhanta. This has sophisticated trigonometry, accurate planetary models, uses mathematical tools such as the sine table, a clear transition from ancient to medieval astronomy. This is the playground of today's mathematician, and would have been seen as the correct school. And it was, of course, later developed and improved by Brahmagupta. No spoilers. So the keen-eared amongst you will notice that there are some missing names. So let's just check which Indian mathematicians we've been talking about over the last few months. Pingala was not an astronomer, possibly not even a mathematician. Umaswati, arguably more of a cosmologist than an astronomer. There's definitely crossover, but he does not really fit the schools. Nabu Ramani and Kidainu, their ideas went west before coming back east via the Greek influence, so they're in there somewhere but not really formally named. No, you say. Of course those guys are not in the taxonomy, but what about Aryabhata? Last episode I spent 45 minutes extolling the virtues of Aryabhata, and then Varāhamihira misses him from the list. Why? Well, it's likely because his work was still recent enough that it didn't fit the mould of reviewing ancient schools. In fact, later commentators would point to the sixth school, Aryabhata, as Aryabhata's system. Sometimes you can't write history whilst it's still happening, so we can cut Varāhamihira some slack. But that more or less sums up Varāhamihira's mathematical contributions. Now, I could talk ad nauseum about the 100-chapter textbook on everything. We didn't even get onto perfumes and omens. But I just wanted to give you a little flavour of his work. You might be thinking then that he shouldn't really count as a mathematician if he wrote one rambling textbook about everything and one short history of maths and another textbook on astrology, which we haven't even touched in this episode. But I would like you to think differently. His academic model of collecting and classifying data to make reasoned predictions of future events definitely fits him into the category of scientist, tick. And I'm going to make the bold assertion, strong opinion warning here, that we should consider him to be one of the world's first statisticians. If you agree, then let me know in the comments. If you think there is someone on the internet who has said something that's not true, make sure you tell everyone else what a moron I am in the comments. But, kind listener, I can't leave you here on that bombshell that we might not have talked about any maths, so I'm going to squeeze in one more mathematician as the promised double bill. Bhāskara I. But first, I went to a conference recently on the importance of brevity. Right, back to Bhāskara I. Born around 600 CE in the Deccan region, he is one of the scholars that picked up the story from Aryabhata. As you may remember, Aryabhata wrote his work in verse, in fact only around 100 verses to explain his entire philosophy. Thanks man, really helpful. This brevity helps it stay memorable, but not wildly decipherable. Enter Bhāskara I, a major fanboy of Aryabhata who made his life's mission to explain and preserve Aryabhata's work. For instance, he rewrote much of the original work using a decimal place value notation, and this is one of the earliest explicit uses of such a thing. Yes, we like that. You might recall that Aryabhata definitely used decimal place value, but he used words with suffixes to explain the place value itself. But here we actually have some numbers. Oh my goodness, the history of maths has got to episode 59 and we've only just started using recognizable numbers. Okay, calm down. Let's be professional again. He made a strong defense of Aryabhata's claim that the daily motion of the stars is caused by the Earth's rotation. Think about that for a minute. The stars don't move at all, and the reason they all seem to move at the same speed is because actually it's us that's moving. This is not a new claim by any stretch. Obviously, Aryabhata said it first, but it's still quite cool to have this as such an early point in history. But his most fun and novel contribution has to be the approximation of sine x. Now, obviously, it's not sine x. I feel like I'm second-guessing myself on everything I say about this guy. So they would have worked in the jar system, which we discussed in great detail last week. But forget all of that. Let's just talk about what he's really saying, and that is the approximation of sine x. Makes it a lot more cool. Okay, so this is a big formula. Grab a pen and write this down. You ready? Sine x is equal to, big fraction now, numerator, 16x brackets pi subtract x. Denominator, 5 pi squared, subtract 4x, brackets, pi take away x. So, for those of you who have a podcast player but no pen, what I just read out was a fraction of two quadratic functions. Interestingly, they both involve pi, which we do have a good approximation for now. Now, this matches the true value of sine in the region from 0 to pi, with an error no greater than 1.9%. Stunning. He gives the credit to Aryabhata, but the formulation is his own work. So this is a really, really impressive approximation of sine. By all means, go look this up on Wikipedia, take it over to Desmos, plug it in alongside the sine x, and hopefully you will be as amazed and bamboozled as I was when I typed that in. Now, it's clear from his writing that he also believed pi was irrational, even if that word itself didn't have a formal appreciation at the time. So this just gets cooler and cooler. And it says here in my notes that he was the first mathematician to work with quadrilaterals of 4 unequal and non-parallel sides. Although I'm not going to give the context of this, truth be told, Bhaskara was born slightly after Brahmagupta, so their work overlapped. But thematically, it made more sense to link Bhaskara with the history of Aryabhata. This Brahmagupta guy I keep hearing about will need this whole other episode, so we'll deal with the quadrilaterals of unequal non-parallel sides next time. So, I guess that's it. It's the summer. We all want to stop researching and get outside. Let's end today's episode here. Keep it short and sweet. Next time, bring a packed lunch, because it will be a big one with Brahmagupta. Until then, please come and talk to me on Blue Sky at mathematicians-pod, or you can even find me on Reddit these days, mathematicians-pod, where I'm telling maths jokes, or drop a few quid in my bucket over at www.ko-fi.com/Benjamin Cornish. I also might try a call to action this week. So this is where I tell you to do something and you have to do it. That's the rules, that's the law. So first up, if you are listening to this episode but have not yet clicked the subscribe button, go ahead and smash that into the ground. It really gives me the encouragement to keep going. And if you are subscribed, then go and find your friend who struggles the most to get to sleep at night and tell them to listen to the show. But of course, you won't hear this call to action, because by now I'm sure you've already gone to sleep. Good night, little one. I'll see you next time. Bye-bye. The music today is Dance Macabre Finale by Kevin MacLeod. You can find more information in the show notes.